In this video, we're going to talk about what we call zeros of polynomial functions. Before we do that, we need to review the division algorithm because this division algorithm is basically the basis of everything that we're going to do in this section. All right. So the division algorithm comes from dividing two numbers. For instance, if I divided 17, if I wanted to do 17 divided by 6, right? And let's say that we were going to use long division. So I would put my 6 out here, that's my divisor, and 17 is my dividend, right? I see how many times the 6 go into 1. There, it doesn't go evenly into 1 any number of times or any whole number of times. Or more than a whole number of times. And so we add the next digit, how many times does 6 go into 17? And that's at most 2 times. So we write 2, and then we go back and multiply 2 and 6. We get 12. We do a subtraction, and we get 5, right? This is my quotient. This is my remainder. This is my divisor. And we call this our dividend, but we're going to call this P here, right? And so what we could do is we could write 17 over 6 as 2 and 5/6. All right, now when we write mixed numbers, there's an understanding that that's 2 plus 5/6. And remember, that's your quotient here, which is this Q, plus your remainder, 5, over your 6, which is your divisor. All right, so your division algorithm basically says that you're guaranteed that when you divide a number by another number, then there exists 2 additional numbers such that you can write that division as your quotient plus your remainder over your divisor. All right, that's the guarantee of the division algorithm. Now, the division algorithm actually is written with just this numerator here, this P of X, your dividend. Basically, I can multiply both sides by this equation by your divisor, the number that you're dividing that polynomial P by. And on my left-hand side, they're going to cancel, and I get P of X. But on my right-hand side, I have got to use my distributive property. And so when I distribute it to that first term, I get Q of X times D of X. And when I distribute it to the second term, the D of X cancels, right? And so I get just R of X. So this is the normal way that we write our division algorithm. And actually, we're going to come back to using this way because this is going to be related to helping us find zeros of polynomial functions. And that's the main topic of this section, zeros of polynomial functions. But we're going to do a lot of division, and we're going to talk about a lot of theorems that help us get to finding those zeros. Therefore, I need you to pay very close attention. Sometimes this gets very abstract, and you may not know why we're doing stuff, so please pay attention as we continue to move forward. Now, what we did when we had polynomials before, when we divided a polynomial and by another polynomial, we used long division in order to help us find that polynomial Q of X, your quotient, and R of X, which is your remainder. Well, in this section, especially with polynomials, finding zeros of polynomials, we're going to use synthetic division, all right? Now, synthetic division only works for specific types of divisions of polynomials, right? So this is what it says. Synthetic division is a division procedure used to divide polynomials of the form P of X equals A sub n, X to the n plus blah, 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 right? Remember, this is our general form of writing polynomials. It looks very technical, but basically it's a number. It's a sum of terms that are basically power functions or a coefficient or a number multiplied by your input variable X raised to some whole number power. Right? It's the sum of those terms. We can only use synthetic division if we have a polynomial that's going to be divided by a polynomial that looks like this. It's basically a linear binomial where it's linear because it's x to the first power, and you're going to have x minus some number. And this number c is going to be used in the synthetic division algorithm, and so that's why we write it as x minus c. It's very important. And it's important that we know what is subtracted from x because we're going to use that in our synthetic division. So let's talk about how we're going to use synthetic division, right? The first thing that we do is we write our dividend and divisors in descending order. That means from the highest power to the lowest power. And we're going to always fill in zeros for missing powers of x, all right? Then we're going to create a synthetic division chart using C and the coefficients of the dividend. And then once we set the chart up, we're ready to perform synthetic division, and that includes repeated multiplication and subtraction. All right. Synthetic division is a shortened version of long division. It takes the numbers without the variable parts of long division, which simplifies it, makes it look a lot easier, and then you could still come up with your quotient and your remainder. Let's look at synthetic division in a couple of examples. Let's find the quotient and remainder using synthetic division. I have this polynomial, which is my dividend, divided by this polynomial, which is my divisor. I know that I can use synthetic division because I know that this x plus 1, the x plus 1 is the same thing as x minus -1, right? And so here, my c for synthetic division, what I'm dividing by, is actually a -1, right? Notice that my numerator is in descending order. I have something to the third power, the second power, the first power, and the zero power, right? Our constant term is x to the zero power. And so I have that there, and my denominator is also written in descending order. So I'm in the perfect space to create my synthetic division chart, which is the step 2 here. When we do that, we're going to put our C out front. I like to put a little box almost, and then I'm going to put the coefficients of my numerator or my dividend. I'm going to leave a space because I'm going to write some stuff here, and I'm going to put a horizontal line, and I'm going to start the process of doing synthetic division. The first thing I do is I bring down this first number here, -3. Then I'm going to multiply. -1 times -3 is a +3, and I'm going to put that under 5. Then I'm going to do addition. 5 plus 3 is 8. Now I'm going to start that process over again. -1 times 8 is -8. Once I put it there, I add it to that next term, to the term above it, which is a -14. I start the process over again. -14 times -1 is a +14. Add those things together, and I get 15. At this point, I separate the 15 from the other terms, and I try to figure out what this means, right? And so to figure out what this means, I've placed the work that I would use with long division. Remember, we've already done long division. I'm not reviewing that in this video. If you want a review of that, I think you can go to section P.5, and that'll give you a review of that. Our operations with polynomials, sorry. But what I want you to notice is that these numbers here, the -3, the 8, and the -14, they are the values of your coefficients in your quotient. So these values here, all right, these values are the coefficients of the quotient. When you write your quotient, right, notice my numerator, my dividend was a 3rd degree polynomial, or 3 as the exponent. Your dividend, or sorry, your quotient is always going to be 1 degree less because you divide it by this x to the first power. So it's just going to reduce your exponent in your quotient by 1 unit, right? So this is always 1 degree less than the degree of the dividend. All right? So that is your dividend. If you also notice, this 15 here is this 15 here. So this is your remainder. All right? And so here, this is the remainder. It is always, your remainder always has to be a degree less than your divisor. And since your divisor is to the first power, your remainder has to be to the 0 power. And x to the 0 power is 1, so it's always a constant term, right? And so if I want to write my quotient and my remainder when I'm using my synthetic division, then my quotient, I'm going to just use the Q, is -3x squared plus 8x minus 14, and my remainder is 15, all right? And so basically what the synthetic division is doing, so you can see these numbers appear in your quotient and your remainder, and these numbers here actually come from this subtraction, all right? But it's addition here because you're switching the signs, all right? So instead of doing subtraction like what we would do in synthetic division, remember I would have to distribute my variable here and here, or that negative sign here and here. I would have to distribute this negative sign here and here. I would have to distribute this negative sign here and here. So that would become a +3 here, which I have this positive 3 here. This will become a negative 8 here, which I have a negative 8 there. And this will become a positive 14 here, which is that positive 14 right there, right? So it's basically taking, doing repeated multiplication and addition, and taking the numbers out of the long division chart and doing it with synthetic division. All right. But we have our quotient and our remainder. We know our quotient is 1 degree less than the dividend. Our remainder is always a constant. And so let's look at part B here. Now notice here, I have everything in descending order, but I don't have x to the third power. So I'm going to add a 0x cubed, and I don't have an x squared. So I'm going to have a 0x squared, right? So when I set up my long division chart, here my c is 3, right? Because that's what I'm subtracting from the x. So that means c equals 3. So in synthetic division, I'm going to put my 3 out here. Then I'm going to put my coefficients. I have a 2, a negative 5, a 0, a 0, a negative 5, and a 7. Leave some space, bring down by 2, and let's start synthetic division. 3 times 2 is 6. Add 6 and negative 5, I get a positive 1. 3 times 1 is 3. Add those together, I get a positive 3. 3 times 3 is 9. I add those together, I get a 9. 3 times 9 is 27. Add those together, I get 22. 3 times 22 is 66. Add those together, I get, is that a 73? I believe so. And so this is my quotient, and this is my remainder. Remember, our quotient is 1 degree less than our dividend, right? So since this is a 5th degree polynomial for our dividend, our quotient will be 2x to the 4th plus 1x cubed. I'm just going to write that as x cubed plus 3x squared plus 9x plus 22. And our remainder would be 73. So we have our quotient and we have our remainder using synthetic division. So we don't have to go through this process of doing long division, but we always have to remember, we still need to know how to do long division because synthetic division only works when our polynomial is written in the form x minus c. All right, or x plus a number or x minus a number, same thing. All right. Now we're going to talk about some theorems, right? So theorems in math are basically statements that can be proven, all right? And so we have something called the remainder theorem. It says if the polynomial p of x is divided by x minus c, kind of like what we did with synthetic division, then the remainder is actually p of c, right? It's the remainder is exactly the same as just evaluating that function at c, okay? And so that's what this line right here is basically saying. And so I'm going to use synthetic division and the remainder theorem to find g of negative 1 if g of x equals x cubed minus 4x squared plus 8. Now, if I asked you to find g of negative 1 just using your knowledge of functions, okay, and this is what we generally do. I'm going to call this the old way, all right? If you were going to find g of negative 1, what you would do is you would plug in negative 1 everywhere you see an x, right? And so we get negative 1. All right, negative 1 squared is a positive 1, so that'll be a minus 4 plus 8, and we get that g of negative 1 equals 3, right? Well, now that we know synthetic division and this remainder theorem is saying that, oh, I can find g of negative 1. All right, so using this way right here, I can find g of negative 1 by letting negative 1 be c and plugging in, doing the synthetic division on this type of polynomial here. So notice I have x to the third power that has 1, negative 4x squared. I don't have a linear term, so I'm going to put a 0 there. And then I have 8 as my constant term. I set up my synthetic division chart. 1. Negative 1 times 1 is a negative 1. Add those together, I get negative 5. Negative 1 times negative 5 is a positive 5. Add those together, I get a positive 5. Negative 1 times positive 5 is negative 5. Add those together, I get 3. The remainder theorem says if a polynomial p of x is divided by x minus c, notice I'm putting negative 1 for my x minus c, then the remainder is what you get as your function of value. The function of value is your remainder. Notice my remainder here is 3, which means g of negative 1 equals 3, which is the same thing I would have gotten had I done it the old way, right? So that gives us a way to determine what the remainder is when I divide a polynomial. So for one, we get that the remainder is what I get when I evaluate the polynomial at C, all right? We want to remember something about when you divide two numbers, right? When we divide two numbers and we get a remainder of 0, what do we know about B, right? Well, one thing that we know about B, and I'm going to type this up. We know that B divides evenly into A, right? So for instance, if I were to do, let's see, 18 divided by 6, right? 18 divided by 6 goes in at 3 times, right? And it goes in at 3 whole times. It divides evenly into 3, right? There's no remainder. 3 with a remainder of 0, right? That's what we know about 6. 6 divides evenly into 18, right? And I'm using A as my numerator here. We also know that B is a factor of A, right? Because if it divides evenly into it, we can call it a factor, right? Remember, if I look at 18, what are my factors of 18? Well, 1 and 18, 2 and 9, 3 and 6, right? So when we have a remainder of 0, we know that the denominator divides evenly into something, and we know that the denominator is a factor of the thing that we're dividing into, right? Thus, we can use synthetic division and the remainder theorem to determine if x minus c, so now we're going to put synthetic division and the remainder theorem together to determine if x minus c is a factor of a polynomial, and that polynomial is your dividend. Because if we are able to use synthetic division and it divides evenly into 0, it divides evenly, that means we get a remainder of 0, then we know that x minus c is a factor of the actual polynomial. And that's basically the factor theorem. It says the number x minus c, and this is going a bit further, is a 0 of the polynomial function y equals f of x if and only if x minus c is a factor of the polynomial, right? All right. It's a 0, right? Something is a 0 of a polynomial if when you plug it in, you get 0, all right? When you plug it in, you get 0. That means that x equals c is a 0 of that polynomial. And so I'm going to read this theorem again. It says the number x equals c is a 0 of the polynomial y equals p of x if and only if x minus c is a factor of the polynomial. Well, if x minus c is a factor of the polynomial, I'm going to get 0 as the remainder. And I know that I get 0 as a remainder by my remainder theorem. It's exactly the same as plugging in your c, and you're getting a value of 0 when you plug it in, because the remainder theorem says that, oh, you could do the old way and plug in the value c and find your remainder or get the value of your function, but it's the same thing as the remainder when you do the division, all right? And so I'm using that with synthetic division, all that together, in order to help me figure out what a 0 of my polynomial is, right? So this next piece says, with synthetic division and the remainder theorem, I know that if I get a remainder of 0, then x minus c is a factor of the polynomial, right? Because if the remainder is 0, then x minus c divides evenly. The factor theorem states that not only is x minus c a factor of the polynomial, but it is one value that causes my polynomial p of x to equal 0. Thus, we call it a 0. And so that's the topic of this chapter here. It's the zeros of polynomial functions. Zeros of polynomial functions are the same exact thing as x-intercepts, right? Because x-intercepts are the values that make your function equal to 0. The x values that you plug in and you get an output of 0. And so we're going to use this information to determine whether x plus 5 is a factor of the polynomial x cubed plus 8x squared plus 11x minus 20, right? I'm going to use synthetic division. Since we're learning this, my c here is -5. And I'll put my coefficients in my synthetic division chart. I'll go through the process of doing my synthetic division. And when I do my synthetic division, I get a remainder theorem, a remainder of 0. And so since I get a remainder of 0, I know that my polynomial divides evenly into x plus 5 divides evenly into this polynomial here. So I'm going to say yes. All right. If you wanted to, you could also just plug in 5 here, but these numbers are getting a lot bigger and we may not have a calculator. But that you should get 0 when you do that. When you plug in -5 into each of these for x, you should get 0 because it should be the remainder. All right. But I know that this is a factor of the polynomial. X plus 5 is a factor. What I also know, based off of the factor theorem, that -5 is an x-intercept or a 0 of this polynomial. Because if I plug in -5, the remainder is what I get when I plug in -5 into that function. All right, so you actually get both of those things. It says, using your answer to example 3, factor the polynomial completely. All right, I'm going to move this up because I want to see what I just had. All right. And I left a lot of space as though we needed it. All right, so I want to factor this polynomial completely, right? Well, what I just did when I did this synthetic division, I basically just told myself that x cubed plus 8x squared plus 11x minus 20 divided by x plus 5, because my c is -5, so x minus -5 is x plus 5, or I can look at what I divided by there. It equals, well, this is my quotient, which is 1 degree less than my polynomial that I'm dividing into, so it'll be an x squared plus 3x minus 4. Now, my goal is to factor this polynomial right here completely. All right, what I'm going to do is I'm going to realize that just like what we did in, and I'm going to scroll a lot here, that just as we've done up here, we multiply both sides by d of x, our divisor, and we wrote our polynomial that we're dividing into on one side of this equation and everything else on the other. I'm going to do the exact same thing in this example here. I'm going to multiply both sides by x plus 5. When I do that, the x plus 5s on this side cancel, and I get my x cubed plus 8x squared plus 11x minus 20. And my right-hand side is just that product of those two polynomials. Now with this, if I want to factor this polynomial here, then the only thing I have to do is factor this piece here, and that's an easy polynomial to factor. Put an x here, two numbers that multiply to give you -4 but add up to 3, -1 and +4. And look at this, we have this polynomial here factored completely. So what we can do if we want to factor a polynomial completely is we can find the zeros or determine whether a polynomial is a factor by using the synthetic division. We can rewrite it as a product of our quotient and our divisor, and then further factor our quotient, and that'll give us our polynomial in completely factored form. Very interesting. All right, so now let's go to one of the most important theorems in math or in algebra. So important that we call it the fundamental theorem of algebra. All right, it's very simple, actually. It says every polynomial function of positive degree, all right, that means it has to have so f of x equals 0 is a polynomial function, or f of x equals 7 is a polynomial function. Even though it's constant, it falls within the family of polynomial functions. This theorem guarantees or only works for polynomial functions of positive degree. Any constant function can be written as that number times x to the 0, and 0 is not a positive number, right? So your variable has to be basically a natural number. 1, 2, 3, the degree of that polynomial has to be a natural number or a positive degree, all right? The fundamental theorem just says that every polynomial function of positive degree has at least one zero, that means at least one x-intercept if it's real, but 1 0 in the set of complex numbers. All right, now it guarantees it in the set of complex numbers. And so what we don't want to confuse here, all right, I said zeros are formerly known as x-intercepts. X-intercepts are real numbers because it has to be a real number for it to show up on our graph because we use the real number lines to graph, right? There are some zeros that may not be real numbers. And the fundamental theorem is just saying that you want to have at least one zero in the set of complex numbers. Complex numbers are numbers that can be written as a plus bi, where I is an imaginary number and I is the same thing as the square root of -1. All right, that's what the fundamental theorem of algebra basically guarantees. With that, we want to be able to find all zeros of polynomials. Now, the fundamental theorem guarantees at least one. All right, that's all we can prove. Actually, in all actuality, every polynomial has n zeros. All right, polynomials have n zeros. All right, n is the degree of the polynomial, and remember your degree is your highest exponent. This statement that I just wrote is more powerful than the fundamental theorem, but the fundamental theorem, since it is a theorem, that's what we can prove, all right? What we're going to do in this class is we're going to find all n zeros, whether they're real or complex, right? Our goal is to find all of them. The tool that we're going to use to do that is called the rational zero theorem. It says if f of x equals some polynomial, if that is a polynomial with integer coefficients, where a sub n does not equal 0 and a does not equal 0. So we have to have a variable to a positive whole number power in order for this to work. Then every rational zero, that means it's a real number that can be written as a fraction, okay? Every rational zero is of the form p divided by q, where p is a factor of your constant term and q is a factor of your leading coefficient. So your constant term is there. Your, we left off the, this is funny. A sub n x to the n plus. We left that off here, and that's needed, right? We said that a sub n was not equal to 0, right? And so we need a sub n x to the n, but a sub n is your leading coefficient, all right? So every rational zero is of this form. So if our zero of our polynomial is rational, it's going to take this form here. And that's going to be the tool that's going to help us find all of our zeros, all n of our zeros of our polynomial functions. Let's look at an example. It says use the rational zero theorem to find all possible rational zeros. All right, so we're not finding the zeros, we're finding the possible. Notice the key word here, all possible. So we're not going to go through the whole process of finding all of them. We're going to find the possible zeros, right? So it says that all of them are going to be in the form p over q, where p is a factor of your constant term and q is a factor of your leading coefficient, right? So I'm going to find my factors of a sub 0. All right. I'm going to write this slightly different. I'm going to say my possible p's. And I'm going to say my possible q's. Well, the factors of p, I look at this 6 here, right? Well, I want to know the factors of 6. For instance, 1 is a factor of 6, 2 is a factor of 6, 3 is a factor of 6, and 6 is a factor of itself, right? But not only that, but also -1 times -6 is 6, right? So not only is a positive 1 a factor of 6, a -1 is a factor of 6. So I'm going to write it as plus or minus 1. The same thing happens with 2 times 3. A -2 times a -3 will give you a positive 6. So every time I write these factors, I'm going to put a plus or minus with them. My leading coefficient is 1. So my factors of 1 are 1 and -1, right? And so my possible rational zeros are going to be taking all of these values of P and dividing them by all of my values of Q, all right? So I'm going to take this first value of P, which is plus or minus 1, and I'm going to divide it by plus or minus 1. Well, when I divide anything by 1 or negative 1, it becomes the positive or negative of itself, right? So it's going to be a plus or minus 1. I'm going to take my next value of P and divide it by Q. I'm going to get plus or minus 2. The same thing happens for plus or minus 3 and plus or minus 6. So these are all of my possible values of my rational zeros. And so these are numbers that are going to help me get into finding all zeros of my polynomial functions. And I know again that there are n of them, and the fundamental theorem of algebra guarantees that I have at least one. Now we're going to look at an example where we find all the zeros. Notice the difference in instructions here. Use the rational zero theorem to find all possible rational zeros. Here, we're going to find all zeros, whether they're rational or not. What we're going to have to do is we're going to start by finding all of our possible rational zeros, right? So I'm going to start this almost identically as I started the last example. I'm going to look at my possible P's. I'm going to look at my possible Q's, and then I'll get my possible rational zeros. So if I think about my P's, they're the factors of my constant term, which are 1, 3, and 9, and also the negatives of these values. And my Q is possible factors of Q are 1 and 2. So I'm going to use a plus or minus 1 and a plus or minus 2. So I have to do my possible rational zeros. So I take my possible P's and divide them by my possible Q's. When I divide them by plus or minus 1, I'm going to get plus or minus 1, plus or minus 3, and plus or minus 9. Now I have to divide them by plus or minus 2, right? So 1 divided by 2 is 1/2, so I'm going to have a plus or minus 1/2. 3 divided by 2 is 3/2, so I'm going to have a plus or minus 3/2. And then 9 divided by 2 is plus or minus 9/2, right? And so that is what I have there. And now, because that I know that these are my possible zeros, and I want to find all zeros, I need to see which of these values are x-intercepts. Well, the x-intercepts are those that basically have factors, have the associated polynomial x minus c that divides evenly into my original polynomial that I started with. So what we're going to do is we're going to use synthetic division with some of these possible zeros here. Excuse me. And if I get a remainder 0, then I know that the polynomial x minus c divides evenly into that polynomial, and then that value c is 0, because if we get a remainder 0, that's the same thing as plugging in your value c and getting the output of 0. All right. So let's try some values in synthetic division. I'm randomly selecting a value, right? One of the easiest values to select is 1 and -1, right? I'm going to try, well, let's start with the positive first. I think positive is easier, even though we have some coefficient, at least one coefficient that's negative, right? So I'm going to try 1, all right? So I'm going to put 2, 5, 3, 15, and -9 in my synthetic division. All right, bring down my 2. 2 times 1 is 2. Put it there. Add those together, I get 7. 1 times 7 is 7. Add those together, I get 10. 1 times 10 is, all right, this is not looking very promising because I'm getting 25. Add those together, I get 16. All right, since my remainder is not 0, right? So x equals 1 is not a 0. So that means I have to try another number, right? So I already tried -1 and it did not work. So I'm going to try another number and I'm going to try one that works. Sometimes you have to go through the process, okay? So that's 2. I'm going to go back to my original coefficients, but now I'm going to select to use or try to use -3. So I bring down my 2. 2 times -3 is -6. Add those together, I get -1. 3 times -1, -3 times -1 is a +3. Add those together, I get 6. 6 times -3 is -18. Add those together, I get -3. And -3 times -3 is a +9. Add those together, I get 0. So since this equals 0, that's my remainder. When your remainder equals 0 by your remainder theorem, you know that that's the same thing as saying, what's my function called here? W. That means W of -3 equals 0, right? Because the remainder is the same thing you get when you plug in your value into your function. And that's, by definition, that is a 0. X equals -3 is a 0. Not only that, but we also know by the factor theorem that x minus a -3 is a factor of the polynomial that we started with, which was w sub x, right? So that means I'm going to go back and write my w of x. That's 2x to the 5th plus 5x to the 4th plus 3x squared plus 15x minus 9. When I divided that by x minus a -3, that's the same thing as saying x plus 3. My quotient, which was 2x to the 4th minus x cubed, that's my quotient here. So dividend divided by divisor equals your quotient, which I'm writing here, plus your remainder, but my remainder is 0 divided by my divisor, so that's just plus 0, and I'm not going to put it there, okay? And what I could do is I could multiply both sides of this equation by x plus 3, and when I do that, the x plus 3s are going to cancel here, and I'm going to be left with a 2x to the 5th plus 5x to the 4th plus 3x squared plus 15x minus 9 equals this product here. And I'm going to leave it just like this. And you can see why this equals 0, right? Because if I set this polynomial here equal to 0, then I get these two things equal to 0, right? I've just basically factored that polynomial as a product of two factors, right? So if I set this first part equal to 0, I can find my other zeros. And of course, we already found that x plus 3 was a 0. Our -3 was a 0, so that's already there. So what I'm trying to point out to you at this point here is that your other zeros are going to be coming from your quotient. All right, because we could write our original polynomial as your quotient times your dividend, your divisor. Now, the divisor, since it was a divisor, we already have that 0 already. So this 0 is already encapsulated. So this is already here. Our other zeros are going to be coming from our quotient here. So once we do synthetic division and we realize that we have a remainder of 0, then every other 0 is going to always come from our quotient. And so what I'm going to do is, instead of doing synthetic division or trying to solve an equation equals 0 on my original polynomial, I'm going to use my I did something wrong, right? This was to the 4th power. So these exponents here, I am so sorry. You notice I made it work right. These are to the 4th power. That's to the 3rd. That's to the 2nd. That's to the 1st, right? So my exponents here, I copied them down wrong. 4, 3, 2, 1, 0. So this is to the 4th power. This is to the 3rd power. This is to the 2nd power. That's to the 1st power, right? So when I get to my dividend, I just messed that all the way up. Sorry. Some of you are probably like, what is going on? All right. So when I get here, and I knew it was an error because when I got here, I'm not able to solve that very nicely. All right. So since my dividend was to the 4th power, then this stuff is going to be to the 3rd power. So this should be a 3 and that should be a 2. Okay. But what I was trying to say before I caught that error, right? And so remember, I make mistakes too, was that once we find that one number is a zero or it divides evenly into a polynomial, then our next, when we try to find our other zeros, we're going to use the quotient. And my quotient is 1 degree less than my dividend. So I should have known at that point that this is going to be a third degree polynomial. And notice I could use synthetic division to find the zeros of this polynomial here by finding my values of p over q. Or actually, I could use some of these same values that I have here to find my other zero. Or if you notice, this polynomial has 4 terms. And so if I'm comfortable trying to factor where a polynomial that has 4 terms, and it looks like this can be factored by grouping, then I'm going to do that. So I can find my other zeros by using the method that doesn't involve synthetic division. If I don't want to do that, I can continue synthetic division, but instead of using the coefficients of my original function, I'm going to use the coefficients of my quotient, all right? I'm going to use the coefficients of my quotient. Let's solve this by factoring out the x squared from these 2 terms. I get a 2x minus 1. Factor out a 3 here, I get a 2x minus 1. And since both of those have a 2x minus 1 as a factor, I get x squared plus 3. So that's a product of 2 things equaling 0. And so I get 2x minus 1 equals 0, or x squared plus 3 equals 0. Those are going to give me my other 2 solutions. I get 2x equals negative 1, divide both sides by 2, I get negative 1/2. Here, I subtract 3 from both sides, I get negative 3. We take the square root of both sides, and we get x equals plus or minus 3, the square root of 3, and then that's an I because that's a negative under that radical, right? And so we have 1, 2, 3, 4 solutions. And those are the solutions to my polynomial. You can write these 2 separately, but as I said before, we're going to find all n zeros, and n is 4 there. Now, I chose to use factoring once I saw that what my quotient was, right? So you don't have to go through this process of writing all of this out. I just did this so that you can see that I'm going to use my quotient to find my other zeros, right? What you could do is you can use, and I'm going to do that here before we finish this video. I know it's getting long. I'm going to try another number. We found out that negative 1/2 was another zero, so I'm kind of cheating here. But I'm going to use that in synthetic division using my quotient. I just want you to be able to see this. I bring down my 2. 2 times negative 1/2 is a negative 1. Add those together, I get a negative 2. Add those to 2 times a negative 1/2 is a negative 1. Add those together, I get a negative 2. Here, I get a positive 1. Add those together, I get a 7. I made a mistake. Another mistake. I must be tired today. When I add 1, I have to add 1 to both sides here. That's a positive. That's a positive. I got here, and I realized that this was not going to make a remainder of 0. So excuse that. Let's go here. 2, negative 1, 6, and negative 3. All right. Let's bring this down. That's a 2. 2 times a 1/2 is a 1. Add those together. We get 0. Now this is going to work. 0 times 1/2 is 0. Add those together. I get 6. 6 times 1/2 is 3. Add those together. I get a remainder of 0, right? And so since I got a remainder of 0, I know that x equals, this is a 0 of my polynomial. X equals 1/2. And then my quotient, now since this was to the 3rd power, my remaining quotient is to the 2nd power. And if I want to find that 0, then I'm going to have to come back to a regular equation, because I can try synthetic division as with all of my other rational zeros. And I'm going to see here that the only way I'm going to get my other zeros is for me to solve this quadratic equation. And so generally, I wrote it plus or minus the square root of 3 times I. Generally, we like to tell people to do synthetic division until you get to 3 terms in your quotient which means you have a quadratic equation. And when you have a quadratic equation, you can use the quadratic formula or completing the square, and they'll always give you your last two solutions. So generally, I'm just going to recap, right? Find all of your possible zeros, your possible rational zeros, by doing the p's over q's, right? The factors of p, factors of q, and the possible rational zeros are your possible p's over q's. Try them in synthetic division, right? Once you find that one of them is a zero, use the quotient and do synthetic division on that quotient to find your other zeros. So we did -3. Don't worry about this stuff here. In practice, you don't have to do that. Try other numbers using your quotient. I tried to do -1/2. That did not work. So then I went to 1/2, right? When I went to that 1/2, I got another zero remainder. So I knew that x equals 1/2 was a zero. And now I stopped with synthetic division. And you can keep going, but I think it's a waste of time to keep going once you get to a quadratic equation, because we know how to solve every single quadratic equation. If we would have tried all of our other numbers on this thing right here, we would have wasted a bunch of times, because this is a non-real result. All right. And so that concludes this video. I know it is very long, but this topic is very important and it's kind of deep and complicated. As you saw with what I did, it's very easy to make a mistake. If you're going too fast, we're dealing with a lot of numbers, a lot of steps and things of that nature. And so take your time and try your best. See you in the next video.